So, welcome back. So, we continue with a discussion on the various techniques for low power design. We have seen some methods or techniques which can be used at the level of gates or at the so called RTL level design. We shall also be looking at some architectural and higher level techniques which you can use. So, we basically continue with our discussion what you are talking about last day and look at some other techniques that we can employ or use for reducing the power consumption in a design. Okay. So, other low power design techniques. So, we look at some of the architectural level approaches here. See, architectural level approach means we are not looking at the level of detail where I have the gates and flip flops. We are looking at a slightly higher level, maybe at the register transfer level. We have multipliers, adders, we have a pipeline. We are thinking globally at that level. We are not looking at the level of gates. Okay. So, several such architectural level approaches have been proposed by various people, and some of the methods we shall be explaining the essential idea behind it. These methods can be used again to reduce power. Some of them use parallelism, pipelining, retiming and something called bus segmentation. Now, you will see that many of these techniques they do require some additional hardware. So, you are increasing the cost in terms of area or in terms of number of gates or transistors, but this is quite acceptable nowadays. As I mentioned earlier also, reduction of power has become of paramount importance. Power reduction is sometimes considered to be the primary thing, only after that the other features like performance and things will come. Because you say, if you suddenly go to the market and see that someone is selling a laptop and saying that it can survive 15 hours of battery once you charge it, you will be pretty impressed. So, the other features will become secondary for you, maybe for some time at least. Okay. All right. So, let us look at these methods. So, what they are. So, using parallelism, see, these are very ad hoc approaches. So, we illustrate this concept with the help of a very simple example. Let us take a multiplier. See, the idea is very simple. Suppose in a processor I have a multiplier. The multiplier is supposed to multiply two numbers obviously, and I need or I have some requirement of the required throughput, like I want some certain n number of multiplications to be carried out within a time t. Let us say this is what my requirement is. Suppose I am building a DSP processor which is supposed to compute some operations on some signals which are coming in real time, image, audio, some kind of signals. So, I know what kind of or what is the number of multiplication operations that are required to be carried out per unit time or within a time t. So, I know the delay. So, now I can explore several design alternatives, like let us say I can say that, well, I have a multiplier that is fast enough which can sustain the throughput that is expected. So, this fast multiplier is working with some frequency, let us say f or f reference. Now, I say that, well, let us do something like this. Let us replicate the multiplier. Well, we are not that much worried about increasing the area, because nowadays we can put more hardware on the chip, that is very easy nowadays. So, let us use two multipliers instead of one, okay, and let us share our load between the two multipliers. And what we are doing? We are reducing the frequency by half. See, earlier we are carrying out every multiplication in time delta. Now, each of these multipliers will be carrying out multiplication in time delta by 2. But because there are two multipliers, the total throughput will still be delta, okay, because in this time delta you are finishing 2 multiplications. But because you are reducing the frequency by half, the impact of the power will be much more significant. So, overall power dissipation will go down, and this is the idea. Okay. So, whatever we have mentioned is written here. I have mentioned instead of this instead of one multiplier running at a frequency f ref, we use 2 multipliers, we replicate it and they run at half the clock frequency. So, overall throughput naturally remains the same, and there will be a multiplexer at the output side that will be taking the output alternately from the 2 multipliers and will be generating the results at frequency f ref. Okay. So, something like this. This was my original design. So, where we had let us say 16 by 16 multiplier, 2 numbers A and B were coming, loading into register, they were clocked with a frequency of f ref. So, results were generated one product in time 1 by f ref. But now what I am saying is that we use 2 multipliers with again registers separating them, and they are clocked by a clock whose frequency is half. Let us say one of them we are loading by the leading edge of the clock, rising edge, and the other we are activating by the falling edge of the clock. So, we are supplying 2 sets of data every clock. So, one of them we are feeding to here, other we are feeding to here. Now, because these 2 multipliers are now slower, data are coming at f ref by 2. So, the input data transitions are also happening at a slower rate. So, number of transitions here also will be slower. So, products as they are generated. So, again in the output side you are taking out the products, one at the leading edge, one at the falling edge, one from this, one from this. So, with respect to the final output, the throughput of this circuit remains the same, but with respect to the individual multipliers there are far fewer number of transitions and the power consumption on the average will be less. This is the basic idea in this approach. Second concept involves pipelining. Okay. Let me recall or review the concept of pipelining for those who may have forgotten the basic concepts. So, I am just explaining the basic concept of pipelining first before I go through this. Suppose I have some computation that takes a time, let us say t. So, I have a set of input data, I apply them one by one, I1, I2, I3, and I get the outputs O1, O2, O3. Okay. So, if there are the n number of inputs, so the total time will be n multiplied by t. Now, the concept of pipelining says that I am splitting this computation t into several parts. Okay. For the timing, let us assume that they are all of equal size, means they take equal times. Let us say there are k number of stages, I am dividing into T1, T2, T3, Tk. And for a pipelining, of course, we will be needing some register stages in between, like this. So, data will be fed at one end and they will go like this. Now, the basic idea is that when this input I1 comes, first I1 will be coming to T1, it will get executed, but after some time T1 will be finished. So, this I1, the result will go to T2. Now, T1 can start with I2. then next step I1 will go to T3, then I2 will come here and I3 will come here. So, in this way we can get overlapped execution. So, when n is large, we can get a speed up which is approximately equal to k, equal to number of stages. So, by using pipelining, we can have speed up, we can have more computation per unit time. But here we are talking with respect to power consumption. Let's imagine a scenario like this, that we had a circuit block that was good enough to meet our deadline. We do not want to make it faster. Okay. Now, suppose we break it into two parts in a pipeline, or k parts in general. We make it in a pipeline. So, if we make it in a pipeline, then it can be run faster, but we do not need it to run faster. So, now what we do? We make a pipeline all right, but we run the pipeline at a much slower frequency, such that my overall throughput remains the same as the original, but my average power consumption drastically reduces. Okay. This is the basic idea. So, here we are saying that we are making the pipeline stages simpler. Just like you do, we divide a computation into simpler sub computation, and each of these stages we can either reduce the frequency or we can reduce the voltage, power supply voltage. So, reduction of power supply voltage is also a very important way to reduce the power consumption, because you recall dynamic power is proportional to the square of the voltage. So, the different pipeline stages you can reduce the power supply voltage also, okay, to make it a little slower, and of course, to reduce the power consumption to a great extent. So, this is just a very specific example, you just ignore the figures for the time being. This is for a particular case study. So, with respect to the original voltage, the voltage was reduced to by 1.83 times. So, when it is divided into two equal parts. So, it was something like this. So, there was a multiplier, we divided the multiplier into two parts, first half and the second half in a two stage pipeline. And what we did? We ran the pipeline at the same frequency, but the voltage, initially it was Vref, now it has become Vref by 1.83. So, if you compute the power consumption, so for the power for this new pipeline, new design, the power consumption was about 36% of the original power consumption, because it is square of the voltage, proportional to square of the voltage, and you are reducing this voltage. This is the essential idea, right. So, we are splitting a computation into smaller sub computation in a pipeline, and we are reducing the power supply voltage of these stages, thereby reducing the overall power consumption. Okay. Retiming is something which we talked about earlier, but retiming we had used to earlier we talked about to improve the performance of a design, but now here we are talking about retiming for improving the power dissipation performance. Okay. So, here we shall be looking at retiming for a pipeline design and also retiming for a gate level design with flip flops. Just we shall see some examples. See, here you look at a pipeline like this, there are two registers, there is some combinational circuits in between with delays of 6 nanoseconds and 2 nanoseconds, total is 8, and here it is 4. So, in this pipeline the clock frequency has to be such that the time period should be at least 8 nanoseconds, plus of course, the register delay, setup hold times, all those things will be there. But if we can shift or move C2 here like it is shown here, now your pipeline becomes balanced. 6 nanoseconds and 6 nanoseconds. Now, what I am saying is that here our objective is not to make the pipeline work faster. Suppose I already had a design like this which was good enough to meet my timing requirement. Now, we are saying that we are moving around to make it even more efficient, but this 8 nanosecond is good enough for us, but now we have a scenario where you can work with 6 nanoseconds. But now what I can do, I can again reduce my power supply voltages in these blocks, so that I make these blocks a little slower, so that again I can achieve that time of 8 nanoseconds. This is the basic idea, that I use retiming to make my pipeline more efficient, but to restore or to retain the original timing requirement which is good enough for me, I make the block slower by reducing the power supply, and if I make it, my power will also go down. This is the idea. So, another example I am showing for a gate level design. So, here suppose I have a gate level design like this, some gates with some input flip flops and output flip flop. So, there are 4 gate delays in between. Suppose what I do, these 2 flip flops we move across flip flops and place it here. So, now the delay becomes uniform 2 and 2. So, initially clock cycle was 4 gate delays, but now clock cycle is 2 gate delays. So, again the same thing, now clock can be made faster, but these circuits can be made slower by reducing the supply voltage. So, there are many approaches you can use, because the point to note that is that the power dissipation, particularly the dynamic power dissipation, is proportional to the square of the voltage, and it is proportional to the frequency. So, if you increase the frequency, but if you decrease the voltage, the impact of this decrease will be much more, because it is proportional to the square of that. So, the idea is that you increase the frequency, but increasing frequency is expected to increase the power, but at the same time you decrease the voltage. Decreasing voltage will be having a greater impact of the power. So, overall your dynamic power dissipation will decrease, right. This is the basic idea. Fine. And here the last method we talk about, this is quite interesting. This is with respect to the bus. We are trying to segment a bus. You see, what is a bus? In many designs, in particular the complex designs like a processor, where there are many functional blocks, they want to communicate among themselves. We define a bus, a common shared set of lines through which multiple blocks can communicate among themselves. Right? Now, in a CPU, you may be knowing, in a processor there may be one or multiple such buses between the registers and the ALUs and the memory and so on. The buses are connected to several functional units and they can communicate. Now, in this approach what we are saying is that we are looking at the buses, look at a bus and see whether we can split or partition a bus into a set of simpler buses. This is the basic idea. So, if we can do that, this is called bus segmentation. So, here we are trying to avoid the sharing of resources as much as possible. So, I shall be explaining this. This will lead to smaller switched capacitance because of reduction in fan out. I shall explain this with an example. The example that we take, we explore 2 alternatives. First alternative says we have a single shared bus, a single bus which is connected to all the modules. This will result in a large bus capacitance because for each of the modules there will be a driver and receiver, and because there is a single bus, the length of the bus will also be quite long, resulting in larger parasitic capacitance. Second alternative says you split this bus into two smaller buses. So, bus capacitance will reduce, and also less number of drivers and receivers will be sharing one bus. So, let me explain this with the help of an example. Take a scenario like this. The first case, you see there is a bus which is indicated by this solid line. There are 8 modules which are sharing the bus. There are drivers and receivers, sending and receiving drivers and buffers with all the modules. Let us say when this particular module wants to send some data to this module, then this driver will be activated and this receiver will be enabled. So, this bus is being shared by all the modules. Now, naturally the length of this bus will be long enough because it has to connect all these 8 modules. So, although I have shown it like this, in an actual layout they can be placed one after the other in a long stretch. Okay? The blocks may not be placed one below the other in a real layout. And the other thing is that if you look at a particular block, let us say this driver, the output of this driver is driving so many buffers 1, 2, 3, 4, 5, 6, 7 and also itself 8. So, fan out is 8, right, and because the bus is long, so the parasitic capacitance will be something like C bus. So, in the alternate design what you do, we are saying is that this bus we are splitting into 2 buses. The first bus is connecting only these first 4, the second bus is connecting these 4. Of course, there is an interface to communicating between the buses whenever required. So, obviously, we will be doing this bus partitioning by looking at the data transfer requirements. So, most of the data transfer that are taking place, you want to put them into one bus. Between buses, number of data transfers will be less, that is the idea. Now, if we do this, first thing is that the size or length of each bus will be less because it will be connecting less number of modules. So, the individual parasitic capacitances will be much less, smaller than C bus. Secondly, now each driver, earlier it was driving 8 loads, a fan out of 8, now it is having a fan out of 4 plus this bus interface, much less. So, the parasitic capacitance will be less, C will be less. So, as you can see, by doing this kind of simple partitioning, we are able to reduce not only the parasitic capacitance, but also the load capacitance. Thereby, we are able to reduce the dynamic switching power to a great extent. This is one of the very commonly used and popular technique for reducing power. Now, we have looked at a number of architecture level techniques for reducing power. In our next lecture, we shall be looking at some algorithmic technique. Algorithmic technique means we have not yet designed our circuit. We do not have an architecture as yet. We are yet to design. So, even at an algorithmic level or a behavioral level, what are the techniques that you can follow that will ultimately result in a reduction in power? Those are a few things that we shall be looking at and explaining in our next lecture. So, for now let us stop here. Thank you.